Hello everyone, welcome to this video. In this video, we are going to briefly introduce Chinese Remainder Theorem. In mathematics, the Chinese Remainder Theorem states that if one knows the remainders of the Euclidean division of an integer n by several integers, then one can determine uniquely the remainder of the division of n by the product of these integers under the condition that the divisors are pairwise coprime. No two divisors share a common factor other than 1. More precisely, let first of m second of m to the nth of m be pairwise relatively prime positive integers greater than 1 and first of a second of a to an arbitrary integers. Then the system x congruent to first of a mod first of m x congruent to second of a mod second of m until x congruent to nth of a mod nth of m has a unique solution modulo m is equals to first of m multiplied by second of m multiplied to the nth of m. That is, there is a solution x with m greater than x greater or equals to 0, and all other solutions are congruent modulo m to this solution. Be noted that proof is extremely important in mathematics. Without proving, a proposed idea is just a conjecture or hypothesis. Thus, we need proof to justify that a statement is true. Now we are going into proof section for the Chinese Remainder Theorem. We will prove this theorem with proof by existence. First, let case of big M equals to m over case of small m. For k equals to 1, 2 to the n, case of big M is the product of the moduli except for case of m. Because i's of m and case of m have no common factors greater than 1 when I is not equal to k, it follows that GCD of case of m and case of big M is equal to 1. Therefore, exists case of y and inverse of case of big M modulo case of m, such that case of big M case of y is congruent to 1 mod case of m. X is equals to first of a first of big M first of y plus first second of a second of m second of y until to the nth of a nth of m big M and nth of y. Because case of big M case of y congruent to 1 mod case of m, we see that x is congruent to case of a case of big M case of y, then also congruent to case of a mod case of m for k equals to 1, 2 to the n. We have shown that x is a simultaneous solution to the n congruences. Chinese remainder can be used to solve system of linear congruences. Besides, it's widely used for computing with large integers, as it allows replacing a computation for which one knows a bound on the size of the result by several similar computations on small integers. Let's first try out some examples that Chinese Remainder Theorem can be used to solve. First, we calculate m and case of when we stated in theorem. In the theorem, we know that m is equals to the product of 3 and 5 and 7, and first of big M is m over 3, which is 35, second of big M is m over 5, which is 21, and third of big M is m over 7, which is 15. Next, we compute the inverse. With some computation, we can find that the inverse of 35 modulo 3 is 2, 21 modulo 5 is 1, and 15 modulo 7 is 1. Therefore, x is congruent to first of a big M, first of big M, first of y plus second of a multiplied by second of big M multiplied by second of y plus third of a multiplied by third of big M multiplied by third of y, which is equals to the product of 2 and 25 and 2 plus to the product of 4 and 21 plus product of 1 and 15 and 1, which is equals to 239. and is congruent to 29 mod 105. Therefore, we can find that the possibility value of x is 105x plus 29. We can use Chinese Remainder Theorem to introduce some card trick. I'll discuss one in this video. It's the card trick magic of Lim Tao Shen. Prepare two sets of cards, each of them suits 1 to 4, which ace is 1. Arrange them over from 1 to 4 and 4 to 1. Two pairs of opposite order and turn them over. Then shuffle the card and let others decide which sets to shuffle. In here, shuffle means always to take the card from top and put it on bottom. Every time shuffling, alphabets in keyword Lim Tao Shen should be spelled out accordingly, and the shuffling ends when all of the alphabets in keyword exhausted. As a result, we'll find that after end of a shuffling, we will have two same number cards on the top. Why? Let's denote I as shuffling times of one of the sets we shuffle and R as the other. Since we shuffle two alphabets in Lim Tao Shen exhausted, it's 11 times of shuffling. Hence, L plus R is equals to 11. Let big L denote value of card emerge in sets of L and big R as R. We will find that big L is congruent to L plus 1 mod M and big R is congruent to M minus R mod M. Besides, 11 is congruent to -1 mod 4, so L plus R is congruent to -1 mod M. With expression above, we can derive as below. L plus 1 mod M congruent to -R mod M is congruent to L plus 1 mod M congruent to M minus R mod M. Because big L is congruent to L plus 1 mod M and big R is congruent to M minus R mod M. Therefore, L congruent to R and emerge the same card after shuffling. The first pair is matched because 11 is congruent to -1 mod 4. The following pairs should be matched follow with the same rule. Besides, we should realize the keyword can be chosen as any of length 11 plus 12k2, given k is a non-negative integer because 12 is the product of coprime in the system of linear congruence. Notice that the trick is actually a Chinese Remainder Theorem problem and x is the length of the keyword. By solving the problem and find the value x, you can perform your trick. In conclusion, the keyword can be anything as long as the length of it follows the rule. And finally, if we want to determine length x of keyword for big N numbers of cards in this trick, we just need to solve the following system of linear congruences. X is congruent to -1 mod big N, x is congruent to -1 mod N minus 1, to the x is congruent to -1 mod 2. Now we go to the application part of the Chinese Remainder Theorem, which is RSA decryption. We let that Alice sets up a RSA system with public modulus N is equal to 731 and a public encryption key E is equals to 21. She tell no one that N is equal to 731, which is also equals to 43 multiplied by 17, and D is the 263. She can decrypt message C by evaluating C to the power of 263 mod 731. Since she knows the factorization of N, she can use the split decryption with Chinese Remainder Theorem. Chinese remainder tell if PQ are relatively prime, then X congruent to A mod PQ if and only if X congruent to A mod P and X congruent to A mod Q. Now Bob sent an encrypt message C equals to 568. So evaluate M equals to 568 to the power of 263 mod 731. With previous theorem, we can solve easily by m is congruent to 568 power to the 236 mod 43, m is congruent to 568 power to the 263 mod 17 separately. We find that 568 congruent to 9 mod 43 and 568 congruent to 7 mod 17. Besides, we also know that 263 congruent to 11 mod 42 and 263 also congruent to 7 mod 16. So we can find that m is congruent to 9 to the power of 11 mod 43 and m is also congruent to 7 to the power of 7 mod 17. After the computation, we can find the final, which is m is congruent to 40 mod 43 and m also congruent to 12 mod 17. Now we know m is equals to 43k plus 40. 43k plus 40 is also congruent to 12 mod 17, as both of them is a logical equivalent statement of m. Then 43k is congruent to 6 mod 17 and k is congruent to 12 mod 17. At the end, we find that m is equals to 43 multiplied by 12 plus 40, which is 556. Our lesson is ended here. Okay, thank you. This is the end of the video.